Today, we want to introduce the idea of a vector field. This is just a type of function that assigns a vector to every point in the domain. So a vector field is a function that assigns a vector to each point in the domain. Our domains are going to be R2 or R3. We're going to look at vector fields in R2. So everything's flat and we can draw it, kind of. And then we're going to look at vector fields in R3. So for our purposes, we're going to give vector fields one-letter names like we always name our functions. Although we tend to use capital letters, and we're going to write them as vectors. So F will map R2. I don't want to write it this way. I don't want to write it that way. I just want to say something like capital F with a vector of X, Y. So our input is a point in R2. Our output is going to be a vector in R2. So I'll have, let's say, a function of X, Y, I plus a function X, Y, J. Here's a vector field in R2. Notice that F1 and F2 are scalar functions because I'm using them as components of the vector. So note that F1 and F2 are scalar functions serving as components for our vector. So F1 and F2 are the components of the vector field F. F is the vector field, F1 and F2 are the components of that vector field. We can also do this in R3, just with X, Y, Z and an F3. So in R3, at each point in R3, we will assign a vector in R3. Each point in our domain, we assign a vector. Graphs of vector fields look really weird. It's a bunch of arrows. Graphs of vector fields will just look like a bunch of arrows. Graphs of vector fields just look like fields of vectors. It's like a bunch of vectors all over the place. Let's look at an example, something nice and simple. Here is a constant vector field. This is what a constant vector field will look like. It's 2i plus 1j. At every point x, y, we assign the same vector. So this is a constant vector field. At every point, we see the same vector. At 0, 0, we see the vector 2, 1. So if I'm going to draw a picture of this, here's our x-axis, and here's our y-axis. At every point, we're going to see the same vector, 2i plus 1j. At 0, 0, I see the vector 2i plus 1j. At the point 1, 1, I see the vector 2i plus 1j. Constant vector field. All the vectors are pointing in the same direction. Always the same vector. I've only drawn a bunch of vectors here. What does it look like? 15 vectors, but there are infinitely many vectors. It's this vector everywhere you look. 2, 1, all over. Here's a vector field that's not just constant vectors. It's 2, for the x component, we use 2. For the y component, we use x. This is because the functions f1 and f2 are both functions of x and y. So if you're wondering why the x is there, I decided that the j component of this vector field should look like the function x. So if we draw a picture of this vector field, if I evaluate this vector field at 0, 0, so this didn't come from anywhere, I just made this up. The question always is, why is the x with the j? Because this is just made up. Just made this up. It's the x is with the j for the same reason I called this vector field f. Had to come up with something. So if we evaluate this vector field at the point 0, 0, we get 2i plus 0j. So at the point 0, 0, I go 2i plus 0j, this vector. That's the output there. If I evaluate this vector field at the point 0, 1, I get 2i plus 0j. At the point 0, 1, I draw the vector 2, 0. At the point 0, 2, I have 2i plus 0j. And we start to see what we're gonna get. When y is 0, I'm always drawing this vector. If I go over to the point, if I scoot over to this point at 2, 0 and evaluate the vector field, I get 2i plus 2j. So the x goes where the j is because that's the definition of the vector field. So at the point 2, 2, I plot the point 2i and 2j. At the point 2, 1, I got the point 2i plus 2j. And we can see we're going to get this vector, this 2i plus 2j vector. I just realized my scales were a little bit off. Because here, all the if I look at stuff on the other side, if I look at some negative values, we're going to get some vectors going in the other direction. We see that this vector field does not care about the y value. That's why every time we look at all these different y values, we see the same thing. This vector field does not care about y. That's why when we look at all the y values, we see the same set of vectors. So if I look at things on the other side, if I go to some different x values, let's say f of -2, 0, then I'll get the vector 2i minus 2j. So at -2, 0, at -2, 1, we'll have 2i minus 2j. We're not surprised that we're getting the same thing because this vector field doesn't care about y values. So changing the y coordinate will do nothing to the output of the vector. So we're starting to see this pattern. If I go further out, so for example, at F4, we'll have 2i plus 4j, so it'll be steeper. And we know that we don't have to worry about different y values because this vector field clearly does not care about y, otherwise it would have some y somewhere around here. Also, this vector field has been an accident last semester and I haven't got it repaired. That's why this one is dented. If I look on the other side, if I look at, say, f of -4, 0, you see these are going to get steeper just going in the other direction. So -4, a 2, -4. Any questions? How's everybody okay? So a vector field just means that every point we're assigning a vector. It's just a type of function where at every point we assign a vector. Here are the two things that we care about when we're thinking about a vector field. Number one, what is the flow of the vector field? Imagine the vector field as the current on the surface of water. What is the flow of that vector field? What is the flow of that current? If I take a leaf and just drop it onto the vector field, what kind of path does the vector field naturally produce? So we have two questions that we're going to be, two things that we want to think about in a vector field. What is the flow of the vector field? What kind of path does the vector field create on its own? What kind of path is the vector field describing? Number two thing to think about it. What is the effect of the vector field on some path through the vector field? So if we imagine the vector field as the current on the surface of some water, the flow would be just what happens if we put a leaf in the vector field? What kind of path would it carve? The other thing that we would want to consider is if we have our own path through that across the surface of the water, what is the effect of that flow on our path? Are we going against the current or are we going with the current? Is it pushing us along or is it pushing us back? Moreover, how much is it pushing us along? This is why vector calculus is going to be about, this is a question of the dot product. If the vector field and we are going in the same direction, then we just multiply those two things. It's the product. We'll multiply each other. But if the vector field is at an angle, we're not getting all of that vector field's push. Some of the vector field is pushing us along. Some of the vector field is pushing across us. Or if the vector field is coming directly at us, then the vector field is working directly against us. Or if it's pushing at us at an angle, then some of the vector field is pushing against us, some is not. And that is all taken care of with the dot product. What we care about is the angle between those vectors and where it is between 0 and 180. For a vector field, you think about a vector at every point. You want to think about what is the flow of the vector field, what kind of paths does the vector field describe on its own, and you want to think about what the effect of the vector field is as we go through, as we carve a different path through the vector field. Questions? You don't want to think about that on this problem that you're about to see. This is not a problem of vector type. It's just mass is equal to density times volume. I'm going to cover this up to restrict your ability to think about vector fields and the flow of vector fields.
What is an octave? Oh wait, oh yeah, HJ, 3D octave.